Yeah, I'm going to talk about the construction of conformal filters in 3+1 dimensions. But to put it in context, I'll discuss the phases of quantum chromodynamics a little bit more generally, including a short discussion about the phases that are not conformal. But mostly I'll describe how to construct conformal filters in 3+1 dimensions. Okay, there is some flux of people. Should I wait? Okay. Well, this is a completely different topic, so it doesn't rest on what I did before. So what I'm going to discuss here is the dynamics of Yang-Mills theory with quarks, which in some region develops interesting interacting conformal field theories, and in other regions of parameters of the space of parameters develops some other dynamics. So we'll try to just talk about the symmetries, the nature of the fixed point that we expect, and how to reliably establish the existence of these fixed points. So let me define the theory. So the Lagrangian is, as usual, -1/4g², where g is the Yang-Mills coupling, times a trace of f². And then there are the fermions. So I'm going to assume that there are NF fermions, so NF quarks, in the fundamental representation plus anti-fundamental representation. So we have NF quarks. The quarks psi are in the fundamental representation, and the quarks psi twiddle, which I would also give an index I, index A. This would have index I, and this would have index A. Those are in the anti-fundamental representation of SU and C. And this is also of SU and C. And there are NF of those guys. So A goes from 1 to NF. And there are also NF of those guys. So I goes from 1 to NF. So the Lagrangian is the standard Lagrangian. I'll put a bar here. And then I, A going from 1 to NF of psi twiddle, bar A, D, psi twiddle, A. And finally, there may be a mass term. So I'm going to sometimes describe what happens when we give these guys a mass. So the mass would involve psi and psi twiddle plus the complex conjugate. And there is a matrix here, which has indices in this space of IA. IA. So this is the theory that we're going to describe for a gauge group SU and C. The gauge group is SU and C, and NF quarks. So let's start with some simple observations that were made in the 70s. And then we'll get to some more modern developments. So this is the beta function of the Yang-Mills coupling. This theory has only one coupling, one continuous coupling, which is G. I'm going to ignore the masses. So let's assume that the masses vanish. And this is the beta function for G. This is for, this is for, I wrote it only in one case. Let me write it a little bit more generally for a second. I forgot to write here A and C. I forgot to write this and see it's a typo. So this is the beta function for SUNC with an F flavors. And what you see from this, so we'll have here the phase diagram. So this is an F. And NF starts from 0, that's the minimal number. Then there is 1. Then there is some stuff happening until some n star that we don't know. And then there is another critical number that comes from solving this equation, that this is equal to that. Okay, so one finds that for an F, which is, so the critical number that we get by solving this equation is 11 NC. 11 NC over 2. So that's another interesting point where the beta function vanishes. And then there is something that happens. So these are the special points that we'll have to discuss separately. I'll try to fill out the phases here and talk a little bit about the properties of the conformal filters when they arise. So when this number here is positive, which is what happens for sufficiently large NF, NF bigger than 11 NC over 2, then it doesn't really matter what the higher order corrections are. Because if you start from very small g, because this is positive, when you decrease the energy, g just decreases a little bit until it goes to 0. So if you start from infinitesimal g, as you do your RG, and you decrease the energy, g goes to 0. So it doesn't matter what the higher corrections are in this window. And in this window, we know that g goes to 0 at low energies. So our fixed point has g star equals 0. Our fixed point has g star equals 0 in this window. And therefore, this is a theory of free gauge fields, or free gluons if you want, and free quarks. And this conclusion is independent of the properties of higher order corrections to the beta function. At least for infinitesimal g, it always goes back to g equals 0. There is, of course, an interesting and long discussion in the literature about whether there are other fixed points that you might encounter if you start from non-infinitesimal g. Then, of course, the trajectory that g takes depends on these higher order corrections, and you may or may not end up at another fixed point. But here, we just want to make this observation that if you start from small g, then g star equals 0 is a nice infrared fixed point. So I'm going to use a lot the terminology of infrared fixed point versus UV fixed point, and I want to just explain what it means, what I mean when I say infrared fixed point or UV fixed point. So when you have an RG flow, if some CFT occurs at the bottom of the RG flow, meaning that the operator is irrelevant, the RG flow is like that. So from the point of view of this conformal field theory, this operator is irrelevant because it decays. But from the point of view of this conformal field theory, this operator is relevant because it takes you out of the conformal field theory. So this is a UV fixed point, and this is an infrared fixed point. So when we say that g star equals 0 is an infrared fixed point, what we mean is that the operator f squared, which is the Yang-Mills interaction term, is irrelevant. So if you add it with a tiny coefficient, it decays back to 0. Okay, so g star equals 0 is an infrared fixed point, and it's a boring fixed point. Here we have a boring fixed point, it just has free fields. And now we want to discuss this window. This is much more interesting. In this window, at first sight, there is it's very hard to say what's going on because this term is negative. So if you start decreasing the energy, the gauge coupling grows. And if you just take this term in the beta function and you trust it, then it predicts that the gauge coupling would grow ad infinitum, and we don't know what happens eventually. So in this region, the answer might depend on higher order corrections. Whether there is a fixed point or not may depend on the higher order corrections that we've got there. So let's talk a little bit about these higher order corrections. There are two options. Let me parameterize these higher order corrections with a coefficient c, g to the power 5, and then some other terms. There are two options. One is that c is positive, and the other is that c is negative. So let's discuss these two options separately. Let's suppose that c was negative. This discussion is not just hypothetical. I mean, we know what c is, but there are other examples where the signs might change. So it's good to have this discussion, at least a little bit more generally than this specific example. So what would we conclude if c were negative? So if c were negative, I'm going to make two assumptions. One is that c does not vanish at NF, and c equals 11 at NF equals 11 NC over 2. So I'm just going to assume that, this vanishes at some particular value, but there is no reason to expect that this vanishes at exactly the same value. So I'm just going to assume that it doesn't vanish. And then there are two options. Either it's positive at this point or it's negative at this point. Let's assume that it's a negative at this point. So it's negative at NF equals 11 NC over 2. What would we say then? Anybody? How would this diagram change if that were true? Would it change, or anybody just, even if you're not sure, just say something so that there is some, you wake up. It would no longer be infrared free. So here you mean? You mean here?
Well, at the particle that
Right. So there is the question of what happens at exactly that point, and then there is a question of what happens at its vicinity. Right? So we have to separate these two questions. So first of all, about this point, if c is negative, you're right. At this point, strictly speaking, before, we couldn't conclude anything because g didn't run. So if you started from g, which is equal to some specific value at some scale, it doesn't run because at that specific point, this term vanishes. So g doesn't decrease or increase. So if c is negative, at this specific point, what g does is to want to increase towards the infrared. So at this specific point, you lose control, right? However, here, as we argued, the sign of the next term doesn't really matter because if you start from small enough g, this term would always dominate for any point in this window. Okay, so let me try to write the scenario of this case carefully. It's actually not so trivial. So this idea goes back to Caswell, and then Banks and Zaks. And we'll have a separate discussion about c bigger than 0. And this gentleman addressed both options. And they don't lead to, they're slightly non-trivial. So I'm just going to try to explain intuitively what happens in these two scenarios, this one and this one. So let me start from this one. For this scenario, you're right that at this point, at this specific point, the coupling wants to grow, and we don't see any conformal filtering, at least not at first sight. However, I want to have another discussion of what happens in this window, where I argued previously that the sign of the next term doesn't matter. So the point is the following. Here, let's suppose that you're very, very close to this window. Okay? Let's suppose that you're very, very close to this window. There could be a competition between the first term and the second term. Because this is very small. This is order 1. But this is smaller than this. So the idea is that g cubed times a small number could be comparable to the g to the 5th. So you could solve this equation. You could solve this equation and you would find, so this is about this scenario. So for an f bigger than 11nc over 2, we could find a solution which looks like g star squared just by solving this equation. We would find a solution that looks like g star squared is equal to this thing over c. So it's going to be minus 11 over 3 nc plus 2nf over 3 over 4 pi squared in this convention. And this is positive. So it's a good fixed point because g squared always got to be positive. Right, sorry, by c, I guess. Right, without the minus. I think this is okay. This is, here I'm discussing the scenario that c is negative indeed. So minus c, you're right. You're right. Good. So this is a fixed point that you encounter here. There is a question whether this fixed point is reliable. So first of all, we have to discuss whether this fixed point is UV fixed point or infrared. Is a UV fixed point or an infrared fixed point? So the first point is that this fixed point is a UV fixed point. Now I'm going to explain why. The reason is what we said before, that g star equals 0 is a good infrared fixed point here, always. Because if g is sufficiently small and infinitesimally small, it would always flow back to 0. So here we now found another fixed point, but if we perturb it, we decrease g, we add a perturbation that decreases g, then it will flow to this fixed point. So in this scenario, there is a UV fixed point for an f bigger than 11 nc over 2. And that's called the Caswell-Bank-Zaks fixed point. Now, at the time when this idea appeared, people didn't trust it. People didn't trust it because what have we done? We canceled the, let's say, 2-loop contribution to the beta function with the 1-loop contribution to the beta function. And this doesn't seem very reliable. It doesn't seem like a very controllable procedure because there are the 3-loop contributions, 4-loop contributions. So why did we decide to cancel those guys? And so the next idea that appeared in this field, we explained that this is actually a good thing to do, is the following. So the main idea, I just want to write the idea here so that we can get it out of the system. The idea is that it is true that this computation seems unreliable. However, you can ignore higher order terms if you are very, very close to the window here. How can you get very close to the window? If you have an f and an c, which are some integer numbers, you can't get very, very close because let's say nc is equal to 3, like in nature. So this is like 16.5. And an f could be 17, but it can't be closer to 16.5 than 17, right? You can't make an f 16.6. But if you take an f and nc to be very large, you take an f and an c to be very, very large, and you keep the ratio fixed, which is sometimes called the Veneziano limit. So in this limit, you can get arbitrarily close to this window. And you can argue that the higher order terms corrections to the beta function would not destabilize this conclusion. So the conclusions that we've made about this fixed point remain correct in this limit. So there is this Veneziano limit where the existence of this UV fixed point can be established unambiguously. So therefore, the correct picture, if C were negative, would have been, and actually C is negative in some interesting variations of QCD, would have been that there is an infrared fixed point here, which is free, but there is an interesting UV fixed point, which is interacting. So the picture for C negative would have been, let me just draw it here, that we have a UV fixed point, which is interesting and interacting in this regime, and it flows to the G equals 0 fixed point, which is free and boring. Okay. Now, these UV fixed points are interesting for lots of applications in variations of this theory. But this doesn't happen. Yeah. Yeah, very good. So I'll give you an outline of the argument, and maybe the actual argument you could do as a homework exercise or try to read the papers. They're very important. So let me just give you an outline of why this computation is reliable. First of all, intuitively, you want to get as close to the wall as possible. And that's possible when an F and an C are large and the ratio is fixed, then you can get as close as you want to the wall. But more formally, the beta function, let's write the beta function for G. dg over d log mu. So there is an argument due to 't Hooft and then generalized by Veneziano that the way that this function scales when an n and c and an f are very large, right? It's all about the question of how an c and an f appear in higher order terms with what powers. So there is an argument from counting factors of an f and an c in diagrams that implies the following. It implies that if you multiply this g, if you turn this g into g squared, so you just do some little changes of variables, multiplied by n and c, let's say, it doesn't matter which n in the Veneziano limit, then this is a function only of g squared n and an f over nc. This is the scaling in the large n limit, in the asymptotic large n limit, nc limit. So this is a function of the ratio and of g squared n. So each order in the expansion looks like, let's say, the first order looks like g squared n times some function of x. The next order looks like sorry, I didn't mean to write g squared n. I meant to write g squared n squared, because the true-level beta function vanishes. And then there is g squared n cubed times some other function of x, and so on. Okay? Now, your homework exercise is one to understand why this is true. This is a hard problem, but the easier problem is assume that this is true. Prove that in that case you can ignore higher order corrections in the Veneziano limit. And you can therefore reliably establish the existence of this UV fixed point. Okay? So assume that this scaling is true and establish the existence of this UV fixed point if C is positive. C is positive at the transition point. Any other questions? Good. So this is one scenario that is interesting. What does this scenario imply about this region? So here, so if this scenario is true, the beta function at one loop is negative, and also the beta function at two loops is negative. So even if we're close to the wall from the left, the coupling just grows. Both terms are negative, and the coupling just grows, and it doesn't stop. So we don't know what's the infrared fixed point. Here, however, the point of asymptotic freedom is that G star equals 0 is always a good UV fixed point. This is independent of the sign of C. So here, G star equals 0 is the infrared fixed point, but here it's the UV fixed point. And that's what the Nobel Prize for asymptotic freedom is about, right? That the weakly coupled theory of gluons and quarks is always the correct fixed point at very high energies. This is true always throughout this region. So this is always a good UV fixed point. But if C is negative, it just doesn't stop. The coupling keeps growing. Maybe it's stabilized by higher order corrections. We don't know. But we don't see any interesting controlled fixed point. So there are many gauge theories for which this is true, and then the phase diagram is puzzling. We don't know. But it so happens that in QCD, C is positive. So that's the situation in QCD. C is positive when an F is equal to 11 and C over 2. It's some number. It's even in your exercises. I can also quote the number later. I have it in my notes. So we're going to discuss QCD with this, knowing that this is true. And we can now have a more serious discussion of what happens to the left of the wall while we lose control to the right of the wall. So let me draw this diagram again for the case of C positive. Are there any questions about C negative? In C negative, the conclusion, yeah.
Why did you say it's an interacting UV point?
The what?
Why did you say it's an interacting UV point?
Here? Yeah. This point?
Yeah.
This point, this is the G star equals 0 point, which is free. Do you mean which fixed point?
To the right of the wall.
This fixed point is interacting.
And the value of G star is?
Yeah, and the value of G star is this. So this is an interacting UV fixed point that you can realize if C is negative. At least you can realize it in this Veneziano limit, when an F and an C are fixed, and and F over C tends to this value that we have here, which is 11 over 2. So it's fixed and goes to 11 over 2. Okay? So in this limit, we can establish the existence of an interacting for the fixed point. And at least in this little regime, where it's very close to the window, this fixed point is free, is very, very weakly coupled. It's interacting, but weakly coupled because this number is small, if you tune to be very, very close to the window. Now, as you go further and further, this UV fixed point gets further and further from the free fixed point at G star equals 0. So the flow, our G flow, is very, very short near the window. But as you get far away, the flow becomes longer and longer, and we don't know. So it may or may not exist at asymptotically large NF. It's a very hard problem. We don't know. Yeah, you need an antisymmetric tensor. Yeah. Now let's discuss positive C. Let's discuss positive C. Positive C is what happens in nature, so it's more interesting. So I'm going to redraw the diagram. We have 11 over 2 and C, which is 16.5 in real life. We have 0, 1, which are special points. We have another special point that we'll soon discuss. This special point is one of the most interesting challenges for the Bootstrap, which is why I'm discussing this topic. So I want to get to it. And let me just put again all the information that we've already explained. So here, G star equals 0 is an infrared IR fixed point. That we know regardless of the sign of C. Another thing that we know regardless of the sign of C is that here, G star equals 0 is a UV fixed point. Okay? And now I want to assume that C is negative. That C is positive. For positive C, this UV fixed point that we've had before is gone. Because when C is positive, the first term in the beta function is positive, and this is positive, so we don't see any perturbatively accessible fixed point for an F bigger than 11 in C. So here, there is a nice infrared fixed point, but if we crank up the coupling, we don't hit any interesting fixed point in the UV. So we don't see any UV fixed point, but that's okay. We're not so interested in UV fixed points, because UV fixed points require tuning. An infrared fixed point can be more generic because they could be the basin of attraction. So we don't see any UV fixed point in this regime. However, we see something really interesting going to the left, from the left to the left of the wall, right? Because the very same argument we've had before, using the scaling of the beta function at large n, implies that there is now a fixed point obeying exactly this formula, but with a minus sign. So I need to put another minus sign. And here we have now a fixed point. And interestingly, it becomes an infrared fixed point. So the formula would be exactly as before, but with a minus sign. So we'll have 11 over 3 NC minus 2/3 NF over 4 pi squared C. So that's exactly the same formula as before, but now this is an infrared fixed point. So the physical picture here is much more interesting in this case, and that's what happens in QCD. C is positive. But the physical picture here is very interesting. The physical picture is that you start at high energies, which is your UV fixed point, with free quarks and free gauge fields. That's asymptotic freedom. You start scaling down the energy, start coarse graining, doing the energy transformation. G grows due to the one loop beta function. And then the two loop beta function kicks in and stops the growing. And you get an infrared fixed point. So the coupling grows a little bit, then the two loop beta function comes in and freezes it off at this fixed point. So we have an interacting theory of gluons and quarks, and it's a conformal field theory. So there is no scale, there is no confinement. It's a genuine fixed point. It's a little bit like n equals 4. It's an conformal interacting theory of gluons and quarks. So if those of you who work on n equals 4 could think about it a little like n equals 4. Okay? So some interacting theory of gluons and quarks. Without confinement, without mesons, without hadrons, it's a conformal theory. So this is an infrared fixed point conformal field theory. I haven't yet talked about the symmetries very much. I'll soon talk about the symmetries. And the existence of this infrared fixed point can be established rigorously, very close to the wall. So we cannot establish it rigorously for NC equals 3, because we can get to 16.5, only as close as we can with 16. But for large NF and NC, we can get as close as we want, and this formula makes sense. So this leads to a genuinely weakly coupled fixed point of quarks and gluons without supersymmetry. Now, there is a question. Are there any questions about this construction? This is a very important point also in the development of the field. It's a landmark claim or benchmark claim in the development of the dynamics of QCD, that people understood that there is an infrared fixed point here in QCD.
Was this literally a formula to work? You need to assume that C is very large.
That's right, but this follows from the scaling that I've previously described. You remember that I said that if I multiply this by n, then there is a...
C equals 3.
That's right. That's why I'm saying that we can literally establish the existence of this fixed point with small g squared, g star squared, only for a large n.
I thought you were talking about QCD.
Yes, what I'm saying is that we can establish the existence of an infrared fixed point here rigorously in the limit where NC and NF are large, and the ratio is fixed. Fixed and very close to 11 over 2. Now, in QCD, NC is 3, and NF is maybe 16, so they're not so large. The ratio is close to 11 over 2, but it's not quite. So you cannot rigorously establish the existence of this fixed point, but we're going to make a leap and assume that the same is true for NF and NC, which are what we, NC equals 3 and NF is like 16.
But this formula is wrong. It's just existence.
No, this formula is, this formula is correct in the limit where NC and NF are large and the ratio is close to 11 over 2, because then C also scales like some power of n, and this is a very small number, and this fixed point can be established by, it can be established perturbatively, and it's there. For finite NF and NC, I mean, this might be like 0.2, and then you have to decide if 0.2 is large or small, right? So like when you plug NF equals 16 and C equals 3, I'll give you later the value of C. You plug these numbers, maybe it will be 0.2. And you have to decide if you trust 0.2 or not. That's right. At like realistic values of NC and NF, or realistic, I mean, when NF is 16, you should trust the existence rather than the formula. So for a long time in the history of this field, I think that people indeed thought that this is a large N artifact. But now we're pretty sure that it's not. We know that we believe that for NC equals 3, for like NF equals 16, there is a fixed point. We believe that QCD flows to an interacting conformal field theory. I'll just mention the symmetries now. Since we're talking about the massless theory, the symmetries involve rotations of psi's and rotations of psi's twiddles. So the symmetry is just SU and F times SU and F times U1 baryon. So this is the symmetry of this fixed point. This rotates the psi's, this rotates the psi twiddles, and this just gives a phase to psi and psi twiddle, which is opposite. So psi goes to e to the I alpha psi, and psi twiddle goes to e to the minus I alpha psi twiddle. So these are all the symmetries of the fixed point. And then there are some space-time symmetries. But let's not talk about those. So it's believed to be true that QCD for an F equals 16 close to this window flows to such a fixed point. Infrared fixed point. Then there is a question. Are there more questions about this scenario? Yeah.
Sorry, do the centers of
Oh, no. We're not going to discuss this now, okay? Just this is it, the symmetry. This is what's written in the textbooks. If you want to be more sophisticated, I can tell you the answer, but there is no point, okay? So, are there any more questions about the fixed point, the symmetries, and the claim about the fixed point in QCD? Okay, so just to summarize, the claim is that there is such an interacting fixed point. It has not yet been established by the Bootstrap. It's a very interesting open problem, but it should be established by the Bootstrap. We know the symmetries, and at least for an F equals 16, where we are very close to the window, we more or less know the relevant operators, right? We know the G star is slightly irrelevant, but very, very slightly. It's like 4 point something small, because it's an infrared fixed point. We know that the quark mass is going to be a relevant operator. And we know that the quartic is going to be irrelevant. So just to make a table, we believe that I believe that the only relevant operator in this theory is psi-psi twiddle with various indices, I, A. So this operator is going to be a bifundamental of a. So let me make a list of the operators the only operators that I believe are relevant. So one is the quark bilinear. This is a bifundamental of SU and C, SU and F times SU and F. It's a singlet of U1 baryon. And then for NC equals 3, the baryon is probably also relevant. We have psi, 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 and psi, 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 twiddle, twiddle, twiddle. That's just for NC equals 3. For a higher NC, you'll have to take 4 psis, let's say NC psis in general, and NC psi twiddles, and then it's probably irrelevant. But for NC equals 3, this is a fermionic operator. This is a scalar operator. But this is a fermionic operator. And this fermionic operator has charge 3 under U1 baryon, and this has minus 3 under U1 baryon. And it transforms in some representation of SU and F, which is the fundamental representation raised to the power 3 anti-symmetrized. So we could say that this is like something like this, maybe, of SU and F left, of the first SU and F and the second SU and F. And these are probably all the relevant operators. But another striking thing that one should find about this fixed point is that there is an operator which is very, very slightly irrelevant, corresponding to F squared. So these are the relevant operators, and F squared should be irrelevant, but with a very small anomalous dimension. Very, very slightly irrelevant, because the flow is very short. So this is a singlet. In particular, notice that this theory does not have singlets. there are no operators which are singlets of SUNF times SUNF times U1 baryon, which are relevant. And this is something that should be easy to implement, because the condition that there are no singlet operators is rather strong. The first singlet operator is irrelevant. Okay? Next. Are there any questions about the nature of this fixed point? Yeah.
When you say the flow is short, what's the small parameter?
The small parameter is an f over nc. The small parameter is the proximity to the window.
So the anomalous dimension will have an expansion.
Yeah, so the anomalous dimension is obtained in the following way. Yeah, in general, the prescription is that you take the beta function at g star, and you take its derivative. So you study the beta function near g star, you take its derivative, evaluate it at g star, and that's your anomalous dimension. And since what I was saying is that this is an infrared fixed point, means that this derivative is basically positive, but very slightly so. And that the number that appears in this derivative is the anomalous dimension of f squared. So that's the definition of an infrared fixed point.
Would all FF dual?
Great question. Leonardo is asking, what do we know about the dimension of the operator FF dual? I'll answer this question in a second. So f squared is a singlet operator, which is a parity even, time reversal even. There is another interesting singlet operator, which is FF dual. So let's discuss that. Since Leonardo asked, I have an excuse to discuss something I like. So FF dual. So we're studying now the operator F mu nu, F rho sigma, epsilon mu nu, rho sigma. That's another singlet operator, which is invariant under all the symmetries. However, it's time reversal odd. So it's time reversal odd, and that's what distinguishes it from F squared. So what do we know about this operator? Actually, this operator is a descendant. Okay? So what I claim is that this operator is a descendant. It's not a primary operator. It's a descendant of a psi. I'll write a descendant of what? It's a descendant of the following operator. Psi bar gamma mu psi plus psi twiddle bar gamma mu psi twiddle. So that's the U1 axial current. And so this is what you might call the axial current. But because there is an anomaly, the divergence of the axial current has to be FF dual. That's the anomaly equation for the axial current. And by unitarity, the dimension of the axial current has to be bigger than 3 because it's not conserved. And therefore, the dimension of this guy is also bigger than 4. So it's a descendant of an operator of dimension bigger than 3. And therefore, the dimension of this guy has to be also bigger than 4. So this is, again, consistent with what I claim, that this theory cannot have any singlet operators which are relevant. F squared is irrelevant, and also FF dual is irrelevant. Both of them, though, have to be very slightly irrelevant, because the anomaly is very weak at weak coupling. So both of them have to have a very small anomalous dimension, but it has to be positive. It has to be bigger than 4, the dimension. Any other questions about this, the nature of this fixed point? Yeah. Great question. So we're going to discuss that. Any other questions other than what's established on the lattice? Okay. So, as I said, theoretically, we cannot establish the existence of this fixed point except in the Veneziano limit. So we have to resort to numerical tools, unfortunately, for NC equals 3. So for NC equals 3, we have to resort to numerics in lack of a better method. And they would say the following. This is lattice simulations. They would say for an F equals, I think the whole community, as far as I can say, would agree that for the following values, you're OK. There is an infrared fixed point. a non-trivial interacting infrared fixed point. That's what they would say. That they've established this with very little doubt. So n star for nc equals 3 might be 11, might be 10, might be 9. We don't know. And that's one of the central questions for the Bootstrap, right? Because we know the symmetries. The symmetries depend on n star in a very important way. It's like SUNF times SUNF. The representations are more or less always the same, and these operators are always expected to be irrelevant. For FF twiddle, the argument that it's irrelevant is rigorous, because it's from this anomaly business. So n star might be 9, maybe 10, maybe 11. We don't know. Okay, there is some debate in the literature. The different groups claim slightly different answers. Now I would like to just mention what happens below n star, just for the sake of completeness. I think this part is the interesting, determining n star is the interesting problem for Bootstrap. And these are the properties of this conformal field theory. But I just want to mention what happens in the window between 1 and n star, and then I'll tell you what happens for 1. There is an interesting prediction for 1 as well. Any more questions before I discuss n smaller than n star? So the homework problem here is to determine n star. That's a very, very good question.
Sorry, what is the question?
The question is, where would we plug into our Bootstrap equations the information about NC? Okay, that was the question? So what is your answer? What depends on NC in this business?
Nothing directly.
No, that's not true. No, just look at it again. Something depends here on NC. No, the number of boxes here. The number of boxes is NC. Okay? It's a representation of SU and F, but the number of boxes is NC. Because you have to raise the fermion to the power NC to get a baryon. To get a gauge invariant baryon, the number of psi's here is NC. Okay?
For NC bigger than 3, it would be tough.
I don't know if it's tough or easy. For NC, indeed, for NC bigger than 3, these operators would not be relevant, but you could reverse the logic. You could say, what is the first operator in the CFT that carries charge under U1 baryon?
Are there anomalies that you can input? Values of the anomalies?
What is value? Can you explain?
Some 3-point function of currents.
Right, exactly. Leonardo is also perfectly right. We also know the OP coefficients of some currents. So we know the OP coefficient of, so there is an SUNF times SUNF symmetry. And we know the OP coefficient of the JJJ, and here JJJ. And we know some OP coefficients of like J of the baryon, and JJ of SUNF, and J of the baryon, and this SUNF. So lots of OP coefficients are also known, and they also depend on NC, linearly sometimes. So you can throw in these OP coefficients, or you can ask what is the first operator that carries charge under U1 baryon. That depends directly on NC.
What is the reason for which those OP coefficients are known precisely?
They are known from a 't Hooft anomaly matching, because they correspond to a 't Hooft anomalies in the ultraviolet, but they do not get renormalized, these coefficients. There are some structures in JJJ, and one of the structures is an anomaly. So it's protected against renormalization group flow, so you can compute it in the free theory. So some of these OP coefficients have to be the same as in the UV fixed point, G star equals 0. So you can compute them directly. The dimensions of baryons probably get renormalized. In the free theory, they would be like NC over 2. But they probably get renormalized. Yeah.
So the relevant operator is 5, 5, any NC.
Yeah, if NC is
And
the current is not. I didn't list operators. I list if NC is odd, this operator is not a scalar, right? If NC is odd, it's a fermionic operator. So maybe I shouldn't have listed it because I didn't list the currents, but the currents exist indeed. So if you wanted to list the full set of operators which are relevant, presumably it's just this list plus the currents. So maybe that would be good enough. And now maybe this list is exhaustive for NC smaller than 4. For NC bigger than 3 or 4, then probably we should omit these guys. The naive dimension of these guys is kind of on borderline, so it's hard to say if they are going to be relevant or not, but in any case, we more or less know where to look for them. Okay, so let's discuss what happens for n smaller than n star. I don't have much time left, but I do want to say a few words about it.
Is this also being studied for NC equals 2? Is that also a window?
Yeah, NC equals 2 is interesting, but it's a little different because because the representations, the fundamental and anti-fundamental representations are the same. So the symmetry group is not SUNF times SUNF, it's actually SU2NF. Because you can rotate all the quarks. I mean, there's no distinction between fundamental quarks and anti-fundamental quarks. So the symmetry breaking pattern is a little different, and you just have to redo the analysis, but conceptually it's the same thing. This formula still holds for NC equals 2. And NF has to be even by Witten's anomaly, so you can solve. And basically it's the same, you just have to do the analysis of the group theory again. Redo the analysis of the group theory. So let me just mention what happens for an F bigger than 1, smaller than n star. In that case, it's believed that the theory is not conformal anymore. So n star is where we lose conformality. We lose conformality. And and what we have instead is chiral symmetry breaking. So chiral symmetry breaking. So in that case, SUNF times SUNF is going to be conjecturally spontaneously broken to SUNF. That makes sense for an F bigger than 1, right? Because SU1 is empty, so there is nothing to discuss. And U1 baryon is intact. That's what we believe. So we have NF squared minus 1 pions. Okay, that's the regime where we are. N star in real life is presumably 9 or 10 or 11, and we have NF, which is 6.
In principle, you could have confined without chiral symmetry.
Yeah, you could. I'm just saying what's the mainstream view on what this theory does. Indeed, you could. But this is the mainstream view, that there are NF squared minus 1 pions. And the last thing I want to mention, before we discuss more this CFT, I just want to mention what happens for an F equals 1. This is very non-trivial, and it's based on some work that will appear that I'm doing with some people. An F equals 1 is very subtle. I'll explain what happens for an F equals 1 now. I'll be very quick. This is more for the experts. If you don't know the background, then it might be too hard to follow. But I'll just say it anyway for the experts. So an F equals 1 is hard because, first of all, we talked here about the massless theory. The massless theory, in general, is protected by this enhanced symmetry. We have SUNF times SUNF when the quarks are massless, and we can independently rotate the psi's from the psi twiddles. But when there is a mass term, then SUNF times SUNF is broken to the diagonal symmetry because we have to rotate them together. That's comment number 1. Comment number 2 is that if an F is 1, there is no SUNF and there is no SUNF, so the massless point is not distinguished. So what does it mean for the quark to be massless is unclear. So what is this massless point is not distinguished? So it doesn't really make sense to ask the question, what happens to the theory when the quark is massless? Because there is no such thing as massless. The notion of massless is actually not renormalization group invariant. There is additive renormalization. So M is not well defined. So M equals 0 is not well defined. There is no extra symmetry. So it's not well defined. That there is no extra symmetry at the massless point. And therefore, in fact, when you do RG computations, you find that M has additive renormalization. So even if you start at 0, you may move to negative or positive. So there is additive renormalization by logarithm. This setup makes sense for an F bigger than 1, because M equals 0 is distinguished by the appearance of a new non-abelian symmetry, and we can discuss our G flows within this framework. But an F equals 1 is more complicated. So for an F equals 1, we don't talk about M equals 0. Instead, we draw the phase diagram. So this is very much like in our discussions of quantum antiferromagnets. The point M equals 0 in quantum antiferromagnets was not well defined. You remember that there was the mass squared in front of I squared in the Néel VBS transition, and M squared equals 0 wasn't well defined. So NF equals 1 QCD is very similar. We don't specify a specific value. We just draw the phase diagram, and we ask if the transition is first or second order. So I'm going to choose M to be real, because that choice preserves time reversal. So while M equals 0 is not well defined, real M is defined. So if you start from a real value of M, it would remain real under normalization group transformations, because time reversal symmetry is respected by real values of M, but not by complex values of M. So for M, which is real, you can show that for sufficiently large and negative M, there are two vacua, and time reversal symmetry is broken. That has to do with these discrete anomalies that I told you a little bit about in the context of the Néel VBS transition. So you can show that deep for negative M, there are two vacua, and time reversal symmetry is broken. For positive large M, we know that there is one confining vacuum. And there is confinement. There is confinement in both, in fact. So confinement, there is no transition in confining. This confines and this confines. So there is no transition in confinement, but there is a transition in the number of vacua. So it turns out that you can prove analytically that this transition has to be second order. So there is a special point here, but it doesn't have to be at M equals 0, right? Because M equals 0 is not a distinguished point. It's like in LVBS, it might depend on your scheme. But independent of the scheme, there is a special point, and you can prove that the transition is second order. This is a rare case in which we can actually prove that the transition must be second order. This is unlike the quantum antiferromagnet, the LVBS transition, where it's not known if it's second order or first. Here, it's possible to prove that it's second order, and it's dual to the Ising model. So the four-dimensional Ising model. Yeah, it's a free field, free scalar field, also known as the free scalar field. And this free scalar field is actually not just, I mean, it can be identified with something. This free scalar field can be identified with psi twiddle, which is eta prime. So this is the famous eta prime particle, about which there is a strong CP puzzle. So the claim is that with one flavor, QCD, actually, the eta prime particle actually becomes massless. So if eta prime condenses, you break time reversal symmetry, because eta prime is a pseudo scalar. And if eta doesn't condense, you're in this vacuum. So the Lagrangian here is just d eta prime squared plus eta prime squared with some coefficient which is either positive or negative, plus eta prime to the 4. So condensing eta prime breaks time reversal symmetry. Not condensing eta prime gives you're in this vacuum. So that's the proposal, that the eta prime particle becomes massless here. So this, you can think about it as massless eta prime. In QCD, of course, the eta prime is massive for an f bigger than 1, but we claim that for an f equals 1, eta prime is massless. So there is a fixed point for an f equals 1, but it's just a free field fixed point, so it's not so interesting. It's not as interesting as those fixed points. Yet, the story is interesting for other reasons. For an f equals 0, there is no fixed point. The theory is believed to be always confining. And so there isn't much to discuss.
But the eta prime becomes massless at that transition.
Exactly. That's what the claim is. The claim is that eta prime becomes exactly massless. This can be proven analytically. It hasn't been yet tested by lattice simulations, but it should be. It would be tested, I think. It's not so hard. Okay. Are there any questions about either of these regimes? I have reached the end of my time, and yeah.
Normally, it will be until 10:30, but in questions then it will be.
Okay.
The vacuum on the right is trivial?
Yeah. Here the vacuum is trivial. There is no TQFT. And here it's degenerate, and time reversal symmetry is broken. And there are two minima. And there is a domain wall. And the domain wall is a certain Chern-Simons theory plus matter. It's like U1 level 1 plus scalar field. The Chern-Simons theory is described by U1 level 1 plus 1 scalar field. That's what we find. Which I believe is the same as the XY model. But am I right? You know this by heart. Is this the same as? Sorry, this is U1 level n plus a scalar plus a single scalar. Okay, this is the claim. The claim is that there is in this phase there is time reversal symmetry which is spontaneously broken, and the domain wall is U1 level n Chern-Simons theory plus a scalar. That's the universality class of the domain wall theory. So in fact, the domain wall theory has a transition here before you reach this point. So if there is a domain wall, the domain wall becomes a conformal field theory somewhere where the bulk is still gapped, and then the bulk becomes gapless, and you lose the domain wall. Yeah.
Is the balancing of the subleading and the leading term of beta function something that's unique to SQ on Yang mills and fermions, or does it happen for generic means that interesting in people?
Yeah, so there is a question here which is very nice. It's a very nice question. The question is whether the balancing of different orders in perturbation theory is unique to Yang-Mills theory, right? And the answer is, of course, not. I'll give you another small example. I can give you a small example from the Bootstrap, where this is very important. The balancing of different terms is very important, I mean. This is an example which might be familiar from you if you know the Ising model and these kind of things. So let's start from a theory which consists of two decoupled copies of the three-dimensional Ising model, completely decoupled. The dimension of the epsilon operator here, epsilon 1, is 1.41 or 42. I don't know. And the same here, right? So if we now let's deform the action for these two decoupled Ising models by adding epsilon 1, epsilon 2. Let's add this interaction. The dimension of this interaction, the dimension of this operator is the sum of these two numbers. It's like 2.82. So it's not marginal, unlike the gauge coupling, but it's very slightly relevant, right? So if you wrote the beta function, let's call the coupling lambda. So if you wrote the beta function for lambda, the first term would be 3 minus 2.82. So the first term in the beta function would be minus 0.18 lambda. That's the first term in the beta function, just from the tree-level anomalous dimension. And then there is some one-loop correction, lambda squared, with some coefficient. Let's call this coefficient C. Suppose you could prove, and then there are some order lambda cubed corrections, right? Suppose you could prove that C is non-zero and C is positive. So suppose that C is non-zero and positive. Let's say C is 3. So the fixed point would be at lambda, which is 0.18 over C, right? Yeah, this fixed point would be at 0.18 over C. It would be a stable fixed point. And lambda would be small. Like if C is 3, this is a small number. It's like 0.06. And then the higher order corrections would be negligible. You cancel the one loop piece against the tree level piece. And this is negligible. This is like 0.06 to the power 3. So that's already completely negligible. And you can forget about it. And then you can establish more or less with a high degree of confidence, high level of confidence, the existence of a fixed point at positive non-zero lambda. And this would be an infrared fixed point because it used to be, it was a relevant operator. So you started the flow from Ising plus Ising. That was the UV, and then you flew to something. But the flow wasn't very long. The flow is quite short because lambda star is very small. So you flow to some new fixed point, and this is the L2 model. This is the XY model. And indeed, the anomalous dimensions in the XY model and in the Ising model don't differ very much. And that's the explanation. They're obtained from each other by a very short flow. So canceling like different orders is very common. And more generally, the formalism that allows you to study these kind of things is called conformal perturbation theory. You can read about it. There are many reviews, but in particular, we wrote recently a paper with David Simons-Duffin with a long review of conformal perturbation theory. This also allows you to compute C, and this is in your homework exercises, in fact. One of the homework exercises that I wrote was to compute this C. And you can establish this fixed point, and you can match with the critical exponents of O2. It actually works. Any other questions? Yeah.
Hi. So a general question. In 4 plus epsilon dimensions, even with NF equal to 0, there is a infrared fixed point angles there.
You mean UV fixed point? UV fixed point.
UV fixed point, yeah.
But not with an F equals 0.
No, pure angles.
Yeah, that's right.
So I was wondering whether the properties of that fixed point in any way connect to the fixed points of these conformal windows. If by going to higher dimensions, are the phases somehow connected, or do you have any thoughts on that?
I just want to make one comment. I don't know if this is relevant, but once you go away from 4 dimensions, the notion of chiral fermions doesn't exist anymore. And the symmetry of whatever you're doing is not going to be SUNF times SUNF. You don't have any more like these wild fermions. So I'm always bothered. I mean, I'm always kind of apprehensive about this kind of studies of Yang-Mills theory with fermions at other dimensions. Because the symmetry is not manifestly the same, so you might expect to recover the symmetry like accidentally somehow when you send epsilon to 0. But I don't know of any results of this sort. I'm apprehensive because of the axial symmetry, which is very important in 4 dimensions. So I don't know the answer, but I would worry about the axial symmetry. Any other questions? Okay, thanks very much.